In example 2, you want to find the first 3 non-zero terms of the Maclaurin series for cosine x and show that cosine x is approximately this polynomial. Okay, so we'll deal with the second part later. So since we are dealing with x to the power of 4 over here, okay, we will need to differentiate at least 4 times. So you notice that we've written out the derivatives over here, and for the cosine function it's very cyclical, right? Just take note that for f prime x you have a negative sign here. Okay, don't leave that out. And after we differentiate, we need to substitute the values of x equals to 0. So we sub in f0, okay, this is cosine 0, f prime 0 is 0, and so on. Okay, we take all these values and we're going to put this into our Maclaurin series over here. So that leaves us with this particular expansion. And because of the 0 terms over here, you notice that the odd powers of x actually cancel out, and you are left with only the even powers of x. All right. Now, as we are looking at small values of x, okay, the higher powers will actually go towards 0. So at this point in time, we can drop the plus dot 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 and use the approximation sign to show the given result. Okay, so we can now state the final result, and we're done for the first part. Now, in the next part of this example, you want to differentiate this particular result and check whether it matches the Maclaurin series for sine x. Now, why do we want to do this? Because we know that if we differentiate this function, okay, we will get negative sine x over here. So let's take a look at what happens. Okay, so given this result, let's do a differentiation on both sides. So we have negative sine x on this side after differentiating cosine x, and we differentiate this one term by term, so you get this particular expression, right? Let's simplify this a bit, and then now you look at your MF26. On page 2 of MF26, you have this result here for sine x, right? And you check against the terms over here. Hey, your 3 factorial over here is the 6 that is present here, which means to say that yes, the results actually match. And this is why the Maclaurin series is useful, because instead of differentiating the function, it means that I can differentiate its approximation and it will still hold. Okay, so that has, implications on the computing and the generation of solutions for very complicated functions. So let's recap a little bit. All right, this is your Maclaurin series, and we have used the technique of repeated differentiation, where we just find f prime, f double prime, and so on, and we sub x equals to 0. You can imagine that for simple functions, this is pretty straightforward to do, but if we encounter very difficult, complicated functions, then finding f prime and f double prime and so on may not be so straightforward. Okay, so there is another technique for us to find the Maclaurin series, and that has to deal with implicit differentiation. Okay, that means we can expect to use implicit differentiation and still substitute x equals to 0 to find all the necessary derivatives. We will cover this in the next video.